I'll introduce you now and then we can get started. So good afternoon, CGIL. This week we are happy to have Dr. Lucio Mota, a postdoctoral researcher at UNESCO, presenting for us. Dr. Mota is an animal scientist with a master's degree in animal science, specializing in genetics and animal breeding. His research focused on gene expression and proteomics related to residual feed intake in Nelore cattle. He also holds a PhD in genetics and animal breeding, concentrating in the integration of genomic data into reaction norm models. During his PhD, Dr. Mota completed an internship at the University of Wisconsin. Dr. Mota's expertise includes genomic selection, genome-wide association studies, genetic enrichment analysis, and the integration of omics data, statistical methodologies, and machine learning techniques. Currently, he is a postdoctoral researcher at UNESCO, where he works with whole genome sequencing data in Nelore cattle. Additionally, Dr. Mota collaborates on statistical analyses related to large-scale phenotyping and the integration of omics data to identify resilience indicators during the transition period in dairy cattle at the University of Padova. Today, he will be presenting on the genetic factors that impact the quality, efficiency, and sustainability of meat production in Nelore cattle. So, Lucio, I'll turn it over to you, and you can get started whenever you're ready.
Thank you, Gabs, for the good presentation, for introducing me. Hello, everyone. I'm Lucio Mota from São Paulo State University. I'd like first to thank to CGIL for the invitation, the opportunity to discuss today the genetic factors that impact the quality, efficiency, and sustainability of meat production in Nelore cattle. Today, I present and explore how the results from your group here in Jabuticabal have been contributed to developing strategy for increased productivity in Nelore cattle. First, Brazil is the largest country in the South America, with a vast geographical diversity and covering a significant proportion of the South continent. Brazil is strategically located in tropical and subtropical regions, giving a great variability in the weather that ranges from the hot and humid in the Amazonian region to temperate in the southern areas. The rainfall here in Brazil varies significantly, with the wetter conditions in the northern and coastal regions and the dry areas in the mid and central regions here in Brazil and northwest zones here. The precipitation levels are essential for defining the pasture quality and the water availability here in our production system, because our production systems are based on pastures, on few animals, finishing and feedlot systems. This climatic variation here in Brazil causes our pasture to have a seasonal grazing conditions. In the rainy season, the high quality pasture during this season, and low quality of the pasture during the dry season. In some regions of Brazil, this dry season can last up to 7 months of the dry season. These conditions made the Zebul cattle, specifically Nelore cattle, so important to production system here in the tropics. In Brazil, the most predominant breeds is Zebul cattle, particularly Nelore cattle for beef production. The Nelore cattle have a unique genetic and biological characteristics that make them well situated to thrive in the tropical regions, especially their heat tolerance. They have a loose, short hair that usually white or light. How can you see here in these figures? A variation for the color in Nelore cattle. And these hair color have a great important aspect to help reflect sunlight and allows them to tolerate high temperatures observed here in tropical systems, and allows them to tolerate this high temperature and high temperature humidity index. And this colorated is largely determined by a specific chromosome region located on big chromosome 13, have a major region controlling this variability, genetic variability observing hair color, making more white or more gray in some region of the body. Over the past 30 years, there has been significant increase in efficiency of livestock activity here in Brazil, with almost 172% increase in productivity. At the same time, the area of pasture used for the beef cattle production decreased by 16%, reaching about 161 million of hectares in 2023. This is explained by the increased use of technology in livestock farming, such as nutritional strategies, welfare practices, and one of the most important factors was the genetic improvement, which allowed more productivity per animal in the area of pasture. This high productivity is due to the genetic improvement that has been applied to Nelore cattle over the past years. Here in Brazil, the Brazilian cattle head is the largest commercial head in the world, with estimated size of 110 million of animals, which correspond approximately 12% of the world cattle herd. In terms of meat production, Brazil takes the second place with a total of 10.6 million of tons of carcass weight, responsible for producing 13.8% of the beef in the world. Here in Brazil, our production system is predominantly based on pasture, with some animals finished in feedlot. Almost 16.58% are finished in feedlots, and the diets offered for these animals are based on silage and agriculture byproducts, typically for no longer more than 4 months, the period of this feedlot. And now I will introduce a little bit about for the history of Nelore breeding program. Nelore breeding programs or Nelore cattle arrived here in Brazil. Almost 7,000 animals arrived here in Brazil between 1817 and 1962. This period marked the foundation of Nelore cattle here in Brazil. After 1960, the selection criteria for these animals focused on body weight and average daily gain to improve the productivity. In 90s, the first performance and present tests were adopted, allowing for the evaluation of the animals at waning and the early stage. And in 1993, the first genetic evaluation was conducted using the animal model through the blood methodology, which enabled breeders to answer the genetic potential of these heads, improve the productivity and more adaptability for these animals in tropical regions. The target opportunities to improve the beef production efficiency here in Brazil remains in the sustainability intensification strategies with a focus on reproductive traits like heifer pregnancy, age at first count, heifer rebreeding, stability, days to second calving, an important trait to improve the productivity in the herd. And for the side of productive traits, selecting for bar weights at different ages, like a birth, weaning, and the early average daily gain, but also selected for visual score for conformation, precocity, and muscling. Nowadays, have some heads also selected for feed efficiency related traits. Although the reproductive traits in the beginning of the breeding programs and breeding selections for the Nelore cattle are not considered as a selection objective, and are not widely in 1990, but some breeds began to evaluate the reproductive efficiency of Nelore females, which was an important step in initiation, a change in the average age at first calving was approximately 35 months, varying from 28 until 43 months. And nowadays, the age at first calving has been reduced by selection and by testing these heifers for sexual precocity. Nowadays, we have Nelore cattle females with the first calving at 2 years. Passing, nowadays we have 2 regular normal distribution for these traits, and the change of the criteria used by programs, not using more age at first calving, but the probability of these rates become precoce until 30 months. And At the same time, the number of heads and the number of precocious behaviors have been increased along the years. More specifically, in the last 3 years, 2020, 2021 and 2022, the probability of the heifers become pregnant at 14 or 18 months increased a lot. Almost 8%, 80% of the heads had precocious females. And another part for the productivity intensity, when selecting animals for tropical conditions, it's crucial to avoid focusing solely on increasing body weight. Overphasing weight can lead to several negatively correlated responses with bird weight, calving difficulties, increasing mature weight, and maintenance requirements of the animals, reducing reproductive efficiency and production of late maturing and late finished animals. Is a problematic for the Brazilian production system because it's based on pasture. One solution for this was to start selecting animals based on visual score for conformation, precocity, and muscling, which differentiate early and late biotypes of these animals. One example of these selecting animals based on body weight and body weight, only body weight and body weight composition can be illustrated in these two pictures. Here, a biotype selected just for weight. And on the other side, in the left side, we can see animals selected for more balanced traits for carcass, reproduction, and adaptations based on visual score, because the visual score for precocity, conformation, and muscling are well related with these traits. And the quite interesting result for selecting animals for this visual score is that selection is able to genetically improve the weaning and the early performance of these animals without increase the maturity weight of these animals and increase the requirements for the maintenance. Using genomic information, we can see that these heads are little difference in genomic compositions. And we can observe two subgroups based on genomic information, which separated these two kinds of animals, selected just for weight and select for more balanced traits. With the advance on genomics in 2021 marked a transformative period in animal breeding, when complex traits that are difficult to select until this moment effectively started to be explored by breeding programs. Here in Brazil, at the beginning, the breeding program is not also interested in using genomic information, but research was conducted with the main interest of determining whether of genomic selection could be accelerated the genetic improvement and contribute to production better with more efficiently with the aim of encouraging the breeding programs to use this information. And after 2013, some Nelore breeding programs started to use genomic predictions for more balanced selection traits and with a focus on reproduction, was passed from reproduction for age-first calving from selected an indirect selection from directed selection, a selection for carcass traits, and feed efficiency traits. One important application of genomic selection was on meat quality in Nelore here in Brazil, where the key reference population for Nelore cattle, about almost 5,000 animals, was established through a research project led by Dr. Lucio here in Jabuticabal, when promising results in predictive ability were observed for very important traits like meat tenderness and ribeye here in Nelore cattle. And now some breed programs have moved forward and they are routinely collecting this information for some of these traits, like meat tenderness and ribeye and fat deposition. In the near future, they are incorporated more and more programs these traits in their selection index. Here, we can observe the prediction curve obtained for these carcass traits for meat tenderness and ribeye, where the quality good, almost 0.6%, of accuracy for mid-tenderness, and for ribeye, almost 47% of the accuracy with this inclusion of genomic information. Nelore cattle is also being selected for feed efficiency by some breeding programs, and more recently too, some studies have been developed and conducted to investigate the feasibility of selecting Nelore cattle to reduce methane emission. Here on study using different methodology to try and improve it again the accuracy of prediction for feed efficiency traits, because feed efficiency traits represent a key factor for increase the productivity and profitability of the beef cattle production systems, because feed accounts for approximately 50 and 60% of the total cost in the production system. And however, measuring these traits in large scale by breeding programs is costly and a challenge, because we need for specialized equipment and controlled environments. So this is a great opportunity to use genomic selection as a solution by allowing us to predict these traits related to feed efficiency more accurately using a small data set and speed up the genetic progress for feed efficiency in Nelore cattle. Based on this context, we decided to compare the prediction accuracy of machine learning using multi-layer neural network and support vector regression with the traditional parametric methods using for genomic prediction, like Bayesian regressions, Bayes A, Bayes B, Bayes C, Bayesian lasso, single trait GBLUP, and multi-trait GBLUP. For this purpose, we use a population from an experimental Nelore breeding programs. These experimental breeding programs are subjected to different criteria of selection based on bore weight at 78 days. In the first had here Nelore control, the animals are selected for bore weight closer to the mean of the group, contemporary group, in the years. The second and the third heads Nelore selection and Nelore traditional are selected for bore weight. I mean, I select animals with have large bore weight, but since 2013, the Nelore traditional also have been selected for low residual feed intake. These three heads are closed in maintaining a controlling breeding rate. These animals, the animals used here as genotyped with different kinds of finals, with different genotype densities. These animals are inputted, all these animals are inputted to HD panel. The accuracy of imputation was approximately 0.97. It's a very good accuracy. After the imputation, the animals was performed a quality control for a call rate of 90%, a minor frequency allele of 10%, and those that did not meet the hard-Weinberg equilibrium was removed. After this step, a total of 1,024 animals and 3,000 markers remained for the analysis. For evaluated genomic selection, we evaluated using phenotype adjusted for the fixed effect of contemporary groups and animal age as a covariate. We considered the forward validation by splitting the population by year of birth. Animals born from 2004 to 2013 represents the training population, while those born from 2014 and 2015 was served as a validation group. We evaluated different prediction model, considering traditional linear model, like a single trait GBLUP, multi-trait GBLUP, Bayesian radial regression, Bayes A, Bayes B, Bayes C, Bayesian lasso, and non-linear model is more machine learning, support vector regression, and multi-layer neural network. For support vector regression, we consider different different kernel metrics, a linear kernel, a polynomial kernel, and a radial basis function kernel, where we choose the radial basis because the radial basis had better prediction in training data sets against the polynomial and the linear functions. For multi-layer neural network, firstly, we have to apply a dimensional reduction of markers based on GWAS. GWAS results in the training population. We get the training population and train a multi-trait GBLUP and get the best markers explained higher than 0.30% of genetic variance and using as input in the multi-layer neural network. Because multi-layer neural network estimated a lot of hyperparameters, and using the whole genomic information is not possible because it's a very complicated model and very parameterized model too. The training process of machine learning consisted while splitting the training set in 5 folds, where these 5 folds, one round is removed, 1 fold, and used the another 4 folds to training and validate in 1 fold. The hyperparameter set for each model was gamma parameter for support vector regression, and for the multi-layer neural network, we fixed 1,000 epochs and a dropout rate of the 0.2. And for the hyperparameter search, we applied a random search for L1 and L2 regularization and the number of neurons, considering the neural networks. Based on the overall predictive ability, multi-trait GBLUP, multi-layer neural network, and support vector regressions overperformed the another models, the single-trait GBLUP and Bayesian regressions, but we can see here that the best improvements was obtained by multi-trait GBLUP and support vector regression. Here, these improvements varied from 10% until 21%. But how these improvements are so high for some traits and another traits not? For multi-trait GBLUP, the prediction from multi-trait GBLUP were more accurate than those observed by single-trait GBLUP or Bayesian regression because the multi-trait GBLUP has the potential to get some help from the another trait because the traits are correlated. If these traits are correlated and have high correlation, we are able to capture the pleiotropic effect among these traits considered in the multi-trait, and more specifically, when the traits have low heritability, like feed efficiency, residual feed intake, the improvement on prediction accuracy is so high because it gets some help from the ADG and dry mate intake because it have more heritability. For this reason, the prediction ability for feed efficiency was about 21% for multi-trait GBLUP. For support vector regression is a model which are able to capture the non-additive effect and the epistasis effect. For these reasons, they increased predictive ability against the other models. In our conclusions, our results indicated that support vector regression and multi-trait GBLUP approach were more accurate in predicting feed efficiency related traits than multi-layer neural network, Bayesian regression, and single-trait GBLUP. But here in Brazil, we have situation in small populations where we face a challenge where the number of genetic mark often exceeds the number of genotype, the animals, create an imbalance between genetic markers and the animals used to training and validation these equations. While having a numerous genetic markers is essential for capturing variation, it can lead to a higher risk of overfits during the training process because we have a higher number of markers a high number of parameterizations in the model, we have a large number of animals to try to map accurately this genomic information to phenotypic information. To handle this situation, we must balance the efficiency of prediction accuracy using all information or selecting part of these SNP markers as a target to predict the target trait. But the first question is, what strategy should be used for genomic selection to improve prediction accuracy in this situation, where you have a large number of markers and a small number of animals? Use your markers or select markers based on GWAS and other strategies. Trying to solve this question, you compare the predictivity ability of genomic selection using all the genomic information and pre-selecting using two pre-selection strategies, using GWAS and fixation index. Fixation index was chosen because we have three different populations here selected for different criteria. And we used three different groups of the traits, growth traits and ultrasound carcass traits. For this work, we used an experimental population with 1,621 animals from these three different herds. These animals were genotyped with HG and GGP assay with 50K markers. We inputted this information to HG panel and performance quality control. And in the end, we have 1,569 animals and 300,000 SNP markers. The validation scenario used in this study was forward validation, where the reference population was split based on born of the animals. And the reference population encompasses animals born from 2004 until 2018, and the validation population 2019 2020. In this study, we using three different models, GBLUP, BASE-B, and ElasticNet. We use as a target a predictor the adjusted phenotype values. We used two strategies, weighted GWAS. From the weighted GWAS, we used two thresholds based on genetic variance. And the markers explain more than 0.5% of genetic variance, and another group of markers explain more than 1%. The fixation index, the two thresholds was used 0.1 and 0.2. The prediction accuracy was estimated as the correlation between phenotypic adjusted predicted in the validation set and genomic breeding value in the validation set, divided by root square of the heritability of each trait. Comparing the results, the ElasticNet outperformed the another model, GBLUP and BASE-B, improving the prediction accuracy from 8.27% until 14.5% for back fat. This improvement in prediction accuracy may be because ElasticNet combines both penalties from lasso regression and from right regressions, terms on the predictor variables, which help to prevent overfitting and effectively reduce the dimensionality of the markers in the prediction models. But can the selection of markers answer genomic predictions? The answer is yes, because marker selection is important for a small population, but it should be carefully evaluated to avoid negatively affect on prediction accuracy. Like you can see here, the BASE-B reduce selecting marking using the BASE-B. We reduced the prediction accuracy for carcass traits using GWAS. A threshold of GWAS of 0.5% of genetic variance. Here we can see just the reductions for hump fat and the ribeye area for BASE-B using a fixation index using a threshold higher than 0.1. And using the fixation index was more important in this population to increase prediction ability. Almost 4% increased compared to using GWAS, was observed using FST, because we are considering 3 different lines from 3 different selection criteria, and FST help us to find the best SNP markers that are able to differentiate these 3 heads here, head 1, head 2, and head 3. But we select more restrictive thresholds, we can apply GWAS more restrictive threshold. We reduced the prediction accuracy a lot, mainly for base B, and some trait for GBLUP and elastic net. And another situation when select more restrictive threshold for FCT, we just observed the reduction for base B model. What happened when we reduce the number of markers? The first things I wanted to understand was what happened to the genetic relationship between training and validation population, because the correlation between training and validation population is the main factor to increase or reduce the prediction accuracy. When estimating the relationship between training and validation, we observed that applying restrictive thresholds, we decrease this relationship, like you can see here in this situation. Apply more restrictive thresholds, we shrink this relationship between training and validation to 0. Is not able to capture the Mendelian segregation, Mendelian relationship between the training and validation set. Is the main factor affecting this reduction in predictive ability of these models. As a conclusion, we observed that selecting SNP markers based on GWAS results and FST values proved to be beneficial for filtering SNP marker in small population, but when you use a more restricted thresholds for GWAS or fixation index, we can reduce the predictivity ability of these models. Now, we have the problematic of climatic regions here in Brazil. We can see the first slides. We have a very variability on the weather conditions, on the pluviosity and the forage quality. In this review, we highlighted the importance of accounting genotype environment interactions in modern breeding programs and modern breeding strategies to optimize the productivity and sustainability of beef cattle population. And here, now I will show some results from the effect of this variation in climatic regions on the reproductive traits. The reproductive traits or reproductive performance of Nelore heifers is crucial for the profitability and sustainability of beef cattle production system in the tropics. In the tropics, these heifers are often facing the challenge like poor nutrition, high temperatures, and humidity, which cause the genotype environment interaction. That in selecting animals can be more able to be adapted to this higher difference in quality, forage, and the high temperature and variability in the temperature is interesting for the breeding programs. And integrating genomic information in reactonomics help us to identify animals that are able to handle with these situations. For this, we aimed to evaluate how the variation in phenotypic values and breeding values are affected by genotype environment interaction. For this reason, we use the genomic information to try to learn and identify the genomic regions affecting this adaptability of Nelore heifers in these adverse situations in reproduction systems. For this, we use reproductive data measured in 3,079 Nelore heifers. These Nelore heifers are raised in Brazil, Paraguay, Colombia, and Bolivia. The reproductive trait evaluated was heifer early pregnancy, heifer breeding. From these animals evaluated, 21,000 female was genotyped and 1,100 side was genotyped with HD Illumina big sheep. These heifers was inputted to high density genotyping using the F-input. After imputation was applied the quality control filter, and at the end, we remain in the data total of 20,500 genotyped animals and 400,000 markers for reactonorm analysis. The genotype environment interaction analysis was performed in two steps. The first step, we determined the environmental conditions based on contemporary group solution for early weights using the animal model. In the second step, we estimated the linear regression norm, linear reactor norm considering the legend polynomials. We converted the GBV obtained from reactor norm for the intercept and the slope into a snip effect and standard deviation of the snip effect. After this, we combined the snip effect for the intercept obtained for heifer pregnancy HP and for heifer hybrid HR in one using a multi-trait combination, combining the t-values obtained for each intercept for each trait in one single GWAS for the intercept and one single GWAS for the slope value. As the result, here we can observe the genetic correlation for sexual precocity efficiency for heifer early pregnancy and heifer breeding. We can observe the variation was very significantly depending on the environment we take a look. For example, take a look for the high environment where the cats perform better here, but in low inputs or lower environment conditions, the heifers perform not so well compared to when moving for the better conditions for heifer pregnancy and heifer breeding. This correlation indicated for us a higher ranking of these animals and create more mistakes for selecting the best animals. We can see here in the Venn diagrams when select the top 90 animals for low, medium, and high animals, just 40 animals are overlapping these three environmental conditions for heifer pregnancy and heifer breeding. It is an important factor because select animals in poor conditions did not perform well in better conditions. Take a look for the GWAS results for explain how this variability occurs for this heifer for sexual performance and reproductive efficiency. We take a look for the intercept, which represents the mean genetic potential for the sexual precocity, was significant because it affected the gatekeeper for early precocity in Nelore cattle, such as GnRH, signaling, LH, suppression, muscle-fat ratio, and progesterone mediated to oocyte maturation. And we take a look for the slope, which reflects how these animals respond to environmental change. The biological perspectives from GWAS were related to how these animals can challenge with the energy metabolism, energy homeostasis, and growth aspect to respond well with these environment changes. When we take a look at the same GWAS for the another trait, we can observe that this region collectively determine the probability of heifer successfully rebreeding after first calving in the poor conditions and the better conditions. When the conditions is improved, the probability of these heifers become pregnant after the first count have increased a lot. As conclusion from this work, this was highlighted the main aspects of the difference in physiological process related to complex biological interactions between the gonadotropic axis, growth aspect, and sexual hormones, helping to these animals respond to harsh conditions and more advanced environment conditions these animals challenging your growth phase or reproductive phase. Take a look for the genomic information have significantly advanced breeding programs allows to selection for animals with better genetic potential for complex traits. However, new uses for genomics continue to emerge, expanding its application beyond traditional breeding programs goals and to explore the gametic diversity existing between the animals. This represents the variability of an individual, provide extreme projects by recombination of your DNA composition through the crossovers. What is the difference between genetic and gametic variants? Genetic variance refers to the variation we observed in a phenotypic trait in a determined population due to the genetic difference among these animals. If the animals carries homozygous dominant, heterozygous alleles, or homozygous recessive alleles. It's important because it's influence a population potential response to selection. This variance is characteristic of a population and shows how the individuals differ genetically concerning a specific trait. When we take a look for the gametic variance measures the genetic variation we can find in the gametes produced by a determined individual we are selecting. It's indicated the different combinations which each animal can be produced for specific progenies. This diversity observed in gametic variance ensures that each gamete carries a unique combination of determined alleles, promoting genetic variability inside the progeny. We can see here this side can produce more dispersed progenies because this side probably have more recombinations sites producing more diversity gametics for your progenies. When I take a look here, for this side produce less variability in your progeny, probably for the more or less recombination in your DNA. So, what's the origin for the gametic variation? The gametic variation occurs during the reproduction, where alleles can segregate independently into gametes or present recombinations. In independent segregation during the reproduction, the alleles are segregated independently into the gametes. We can see here the allele A, B, and AA produce just one kind of alleles are able to pass for your progeny. When gametic recombinations occur, the probability are increased because we have a situation where occur a crossover of that specific genomic regions, and this specific crossover in that region are able to pass for your progeny, increase the probability you have more recombinations or more combinations of the DNA from sire and from a cow. So to estimate a crossover events, we first calculate the phase of the haplotype, which identifies the parental origin of each allele observed in the progeny. To identify each allele was contributed by father and mother, we analyze the genotype of the progeny. We check the genotype observed in the progeny. You can back this genotype to the parents to try to track these variations in the original genotype from sire or for the done that observed at the progeny. Here we can observe the genotype from the sire and the genotype observed in the progeny, progeny 1 and progeny 2. We can observe here on T and G, you have a break in this region between these two SNPs markers for one individual, indicating recombination sites. In this way, you have the progeny in this region a change of the combinations of the alleles for that specific regions between the two markers. So the crossovers we identified through a crossover by comparing the phase of the haplotypes with the side haplotype or side and haplotypes, depending on the situation you have the genomic data. If you have genomic data for more the side progeny or side progeny in the cow, it's better to estimate the phasing, but it's very accurately to estimate the phasing, also just considering the side and progeny. We calculated the meiosis number, which represents the number of progenes between the pairs of parents and progenes. Calculated the number of crossover is the total number of crossover occurred between the two informative SNPs markers. Here are results from the thesis from one student here from Jaboticabal, where we are evaluating if we have some hotspots, the crossover regions in Nelore cattle. A recombination hotspot is a genomic region where we can observe a significantly higher than the average of the observed in the whole DNA. We can observe some peaks of the recombinations between a specific region in the genome, where we identify higher recombination or lower recombination in this region. Identify because here have a genomic region have more probability to occur for occurring recombination rates, crossover, or other kinds of translation. Just in this region, you take a look in these regions, more blue, have a low probability of recombination. So in these regions, more probably the chromosomes are segregated independently and passed for the progeny. In these regions, are more probability of that chromosome have recombinations to pass for the progeny. Using this information, we calculated the recombination in the Nelore cattle. We observed a total of 2,038 hotspots of these kind of recombinations regions for Nelore size. We identified most of them of these recombinations hotspots on chromosomes 2, 3, 14, and 18. And identifying these recombination hotspots provides a valuable insights into how genetic diversity is generated in the Nelore cattle population, and can, in these insights, can help breeds to optimize selection strategy by creating strategic mating combinations to produce more productive progenies. But the first question for our study, are these hotspots recombination in Nelore cattle heritable? To investigate these, we used two models, one considering the average of numbers of recombination events or hotspot events per side, and another model uses a repeatability model, treating each event as a repeated measurement of side in each project. We observed that the hotspot regions of recombination are heritable in Nelore cattle with moderate heritability, values observed for both recombination rates and number of hotspots with a heritability of 24 and 30% using a model with the average, and using the repeatability model, we observe the 70% and 25% of heritability. And the repeatability values suggest a consistent recombination pattern across multiple progenies, providing a robust evidence of genetic control over these regions, improving the recombination rate in these sites. To try to understand how these events occurred in Nelore cattle, as was analysis was used for the number of hotspot regions, considering the average value and repeatability model as a repeated measurement. We identified 14 genomic regions overlapping there and highlighting their biological importance in maintaining chromosome stability, genetic diversity, and epigenetic regulation is of important factors regulating how the amount of the chromosome regions are able to take recombinations in this population, and they are crucial for gametic variability in this population. As the conclusion from these results, in this study, we characterized the recombination patterns in the Nelore males, identifying a total of 2,000 genetically controlled hotspot regions. These research provide the first recombination map in Nelore cattle, and the next step is to consider how to apply these finds in breeding programs. Now the question is how recombination can be implemented by breeding programs. Recombination significantly boosts genetic variation from the progeny of a given sire, giving breeds more opportunity to select animals with superior traits or superior values for that determined trait. This diversity is essential for improving productivity, adaptability, and long-term sustainability in Nelore cattle breeding programs. And this process begins with the formation of gametes, the sperm and the eggs from the side and then, which carry segregated genetic material reflecting the population variability. These gametes are combined through fertilization to form the progeny, and each progeny has a unique combination of the paternal alleles contributing to gametic diversity and genetic diversity. And understanding how this process occurs, we can directly maintain profile for each specific trait, trying to produce more extreme progenies. Using these results, we can observe the correlation between genetic gametic diversity from different traits. In this example, I used the aged-free scalving to check with the another reproductive trait, heifer pregnancy, heifer breeding, stability, scrotal circumference in male, body weight directly effect, and body weight at maternal effect, IFC with early weight. We can observe it here. We can select animals for these extreme values of correlation between the pair of the progeny for increasing body weight, and at the same time reduce the age-free scalving, and for the another reproductive traits too, because we see the favorable correlation among the gametic variants. These reflect more gain per year selecting for the breeding value for this recombination traits, combining breeding values and gametic values. We can attain more genetic gain compared for the traditional EBVs or APDs for the older traits, and more significantly for the heifer breeding, heifer early pregnancy and stability, more difficult traits, and the gametic variance contribute more for the extreme values for these two traits. And the expected genetic gain using the traditional genetic breeding value or APD using a gametic value combined with ABV, we have increments of 1.14% for ejected Calvin. We have more improvements considering gametic variants than considering the traditional ABVs for the Nelore cattle population. Conclude the remarks for these works, in the last decades, Brazilian livestock sector have experienced a significant increase in productivity, and there are good perspectives for new use of genomic for ensure high productivity in a sustainable way. Genetic improvement has a key role in the sustainability here in the tropics because almost the production is based on pasture. A proper breeding strategy should be applied to optimize use of available resources and to improve the performance of cattle without losing their adaptability for these harsh conditions observed here in tropics. I would like to thank you to the Nelore breeding programs and the funds agents from Brazil, FAPESP, CNPq, and CAPS for the financial support. And again, I'd like to say thank you for the invitation from the CGIL for stay today to present the results from your group here in Jaboticabal. And thank you a lot for your attention.
Thank you very much, Dr. Mota. That was a very interesting overview of breeding strategies in Nelore. I think we'll open the floor now to questions online or in the room here. Do we have any? I think we have one in the room here.
Yes.
You want to go?
Hello, Dr. Lucio. First of all, congratulations for your talk. It's very nice to see how the Brazilian livestock programs are developing during the years. I would like to ask you a question about how about your sustainability traits you presented here, like feed efficiency and methane emission. As you said, Brazil is a predominant pasture-based system. So how do you measure these traits, dry matter intake or methane emission? Are you measuring these traits only in experimental farms, in reference population, or do you have any strategy to measure these traits in pasture systems?
These traits are more evaluated by breeding programs in specific tests, feeding trios, directly in feeding trios, have different feeding trios made these selections and evaluating for feed efficiency. For methane emissions, just 2 breeding programs, one from experimental breeding programs are testing first these methane emission productions to try see if these traits are editable and how the genomic predictions work well. First, then applying the another breeding programs. And the commercial breeding program also integrated the information from feeding trials and methane emissions. Just few farms is still working these collecting data for methane emissions, but the perspective is that be more widely used for the another breeding programs in the next years.
Thank you. Thank you very much, Doctor.
And it looks like Flavio has his hand up. You can go ahead, Flavio.
Yes, can you hear me well?
Yeah.
Thank you so much, Lucio, for the presentation. It was lot of information there. I have just comments and maybe will be a question too. So when you presented the work that you did, look at how to exploit gametic variability or through the recombination rate or select for higher recombination rate. I agree that that's great to identify extreme animals, right? In a breeding program, you would have a more variability of the offspring, and you can identify this animal that are extreme for the traits that you like select for. But you have to remember that animal, when it's used in the production system, is also going to produce more variable progeny. and that for the production system is not good. So there is a kind of dilemma there, right? You select for individuals that have will produce more variable offspring in the breeding part of it to identify the streams, but those streams also are going to transmit, that's the expectation, to the also going to have a more variable progeny, right? And that for the level of the producers is not good. More homogeneous offspring is better for the production system. So how to balance this, I think, is tricky to me. So that's
Yeah, it's
just
a good.
a comment. I don't know if you like to comment, if you
Yeah.
thought about this.
It's a good question about this because we starting to look for the gametic variance, but we not have it planned to yet the result for evaluation how these performance in these extreme variability projects for these diverse situations for the production systems. But the next step is evaluate to this. Check if the animals with higher variability projects from the gametic variance are able also to provide more less affected by this diversity from change from the environment production system.
Yeah, no, I am saying because this, for instance, the recombination rate is heritable. You showed, right?
Yeah.
The gametic variability, because it's associated with recombination, is heritable. So when you select these stream animals based on this gametic variability, they are going to transmit now because you expect they are also going to have more variable offspring. But when it's at the level of the production, that's not the ideal. Like more homogeneous animals. Can is there anyone else that like to ask question? Otherwise, I have another.
You can go ahead, Flavio.
Okay, so my second comment is regarding to the reduction of number of markers. So that you for your genome predictions. So you do the GWAS, you identify the markers that have a more effect, more associated with a single trait or more than one trait. And then you do the genome evaluation. My question for you is, I agree with you that you're going to find higher genetic gain at short term, but did you look at medium and long term, this strategy? And the reason is because with this strategy, we are moving selection pressure on the polygenes to fewer markers, right? So that medium long term, there is simulation studies showing that's not the ideal, right? So I don't know if you had the opportunity there in the studies to look at what we expect at medium and long term with that strategy.
Yes, a good question. You not check this yet, but you try to simulate how this can perform selecting the market from one split more this population in blocked years to check if you are selecting from one year, what's happened. We selecting another year to check this because we don't have it checked yet. But probably yes. But in this situation here, we have three different selection strategies from the head I use it for this work. In this selection is more divergence for the genomic regions. Also too, because one selected for body weight, extreme values for body weight, lower residual feed intake, and another one for the center of the body weight.
Yeah, no, it's just something that we always have to think when you pre-select markers and we put more emphasis on those markers, you have to remove. We are going to remove selection pressure of the polygenes, right? The background genes, and that medium long term is not the ideal. The ideal is to have a kind of a weighting, not just too much pressure on the known these regions or markers that are more associated with the trait. I just want to ask you if you had some results look at this. Very good presentation. Thank you. Thank you so much, Lucy.
Thanks so much, everyone.
Do we have any more questions online or in person here in the room? Doesn't seem like it, so I think we will cut it off there since we're a little bit over time. Thank you very much, Dr. Mota. It was a wonderful presentation, very interesting discussion. And we will be posting this recording online for you to share with your colleagues. And we'll see everyone here next week again for another CGIL seminar. Thank you.
Thank you. Thank you, everyone.